In the last week of October 2025, telescopes across the ecliptic plane recorded a transformation that, for cometary scientists, ranks among the most instructive in recent memory. The interstellar object designated 3IATLAS, already known for its anomalous rich spectrum and low dust-to-gas ratio, entered the inner heliosphere and displayed an unmistakable sun-facing jet, a configuration known as an anti-tail. To the casual observer, an anti-tail appears to defy radiation pressure. The stream of particulate material projects toward the sun rather than away from it. In practice, this is an effect of geometry, not violation. When the observer's sun-comet phase angle approaches 180 degrees, the large refractory dust grains that have recently been released occupy the near plane of the comet's orbit. Scattering sunlight at small forward angles, they generate a linear, sunward pointing brightness feature. For most comets, this geometry is short-lived, but in 3IATLAS the anti-tail persisted for nearly 30 hours of heliocentric motion before collapsing into a conventional tail. High-cadence photometry from the Mauna Kea 2.2M telescope showed a correlated change in brightness of about 0.35 magnitudes during the transition. This suggests the event was not purely geometric, but accompanied by a true alteration in dust ejection morphology. Infrared spectra obtained from the NEO-VISIS extension indicated an enhancement in 4.26 SISBM emission, diagnostic of SIL outgassing. The ratio of CAL to HDANO emission lines rose from roughly 871 to 11:1, far higher than typical Oort cloud comets and consistent with volatile retention in an interstellar origin body. The physics of this transformation is still under analysis, but two hypotheses dominate. The first is that 3IATLAS experienced a localized solar illumination-driven jet emerging from a concavity on the nucleus. As the comet rotated, its sidereal period measured near 11.2 hours. The subsolar point migrated, switching the dominant jet vector by tens of degrees and producing a visible tail reorientation. The second model invokes plasma field coupling. As the comet entered a region of enhanced solar wind density during a minor CME on October 24, charged submicron dust experienced Lorentz force curvature that temporarily reversed apparent tail orientation. Both mechanisms can operate concurrently. What matters for dynamical modeling is that momentum transfer from asymmetric outgassing can impart measurable, non-gravitational acceleration, parameterized by coefficients AT radial, AL transverse, and ALs are normal in the standard Marsden formulation. Preliminary orbit fits using JPL Horizons residuals hint that AL may have increased by roughly 3 tau-10 He a day during the anti-tail phase. Though small, over several weeks such acceleration can displace the osculating trajectory by hundreds of thousands of kilometers. It is this possibility, the minute but cumulative displacement, that triggered the response from the International Asteroid Warning Network, IAWN. Beginning 27th of November 2025, the network's observatories, from Cerro Paranal to Metejon in New Zealand, will coordinate a 2-month astrometric campaign designed to obtain sub-arcsecond positional accuracy through 27th of January 2026. The campaign's objective is simple: test whether 3IATLAS is following a purely Keplerian orbit under solar gravity and radiation pressure, or whether additional forces are at play. The motivation deepened when a handful of private observatories reported residuals inconsistent with the pre-perihelion solution. Using stacked images with 10-second integrations through narrow-band CN filters, they estimated an apparent offset corresponding to roughly 1 million kilometers in the plane of the sky at the comet's distance. Such a deviation, if genuine, would exceed the expected uncertainty envelope from photometric centering alone. But confirmation requires high-precision time, tagged astrometry, corrected for differential refraction and catalog bias, a challenge given that 3IATLAS remains behind the Sun until early November. To interpret such offsets, one must examine the coupling between sublimation physics and rotational dynamics. When volatile ices sublimate, they produce jets that act like small thrusters. The thrust, the tat of half v mrv, where her mrhun is the mass loss rate and v the exhaust velocity of gas molecules. typically 300 ms for coal, for a nucleus radius around of a few kilometers and bulk density near 500 km/pi. The corresponding acceleration, tantasense IAWN, can reach 10 km/s. Over days, this yields measurable orbital displacement. The magnitude and direction vary as the active area rotates, so the resulting trajectory perturbation is quasi-periodic, imprinting a sinusoidal signature in astrometric residuals. Observers will attempt to isolate that signature. Using simultaneous observations from multiple longitudes allows transformation to a heliocentric frame independent of parallax, thereby reducing systematic error. IAWN's campaign will employ both CCD photometry and radar ranging where possible, supplemented by Gaia DR4 reference stars for improved plate solutions. The campaign's data will feed into the NUN, Gravitational Parameter Working Group, which intends to publish a revised orbital solution by February 2026. Yet beyond the mathematics lies a deeper interest, determining whether 3IATLAS behaves like the first two known interstellar visitors, 1T Oumuamua and 2IT Borisov, or whether it represents a new dynamical category. Unlike Oumuamua, whose acceleration lacked detectable outgassing, 3IATLAS displays active volatile release. Unlike Borisov, its compositional ratios and light curve periodicity suggest an irregular shape and heterogeneous crust, possibly the remnant of a differentiated body ejected from another stellar systems in a belt. In this context, the rumored Mars orbiter imagery becomes valuable. A navigation camera aboard the trace gas orbiter was reportedly pointed sunward during a comms blackout calibration and may have captured a faint moving object consistent with 3IATLAS ephemeris. If the data exist, and if the source can be confirmed, photometric modeling could constrain the nucleus's projected cross-section. Preliminary brightness values imply an effective diameter near 3I1 Comet and an albedo of 0.06, remarkably similar to long-period comets, yet dynamically foreign. The physics community now awaits November 310, when the comet is expected to re-emerge from solar conjunction at an elongation of 18 degrees. At that time, it will be accessible to large, aperture instruments capable of measuring both coma morphology and high-resolution spectra of the iron tail. If the anti-tail reappears, scientists will compare its polarization phase curve with that of known comets to deduce grain size distribution. A re-emergent anti-tail would confirm the persistence of large dust aggregates. Its absence would imply that solar radiation pressure has cleared the near-plane debris. As data accumulate, researchers will examine how the comet's non-gravitational forces evolve relative to its rotation phase. If correlations appear, it may be possible to reconstruct the nucleus's spin axis orientation, an essential step toward full thermophysical modeling. Only then can the team quantify whether the observed million-kilometer offset represents real acceleration or merely a transient optical artifact. Until that evidence arrives, 3IATLAS remains both a laboratory and a mystery, a moving test particle through which the sun's electromagnetic breath reveals its invisible structure. When 3IATLAS slipped behind the sun in late October, it entered a regime where solar radiative and plasma forces dominate the evolution of cometary material. In the near-sun environment, particles smaller than about 10 microns experience a delicate interplay of radiation pressure, solar wind drag, and electromagnetic coupling. Understanding the shift from anti-tail to normal tail requires tracing that physics in quantitative terms. In heliocentric coordinates, the acceleration on a dust grain can be written as the vector sum mathmathbefta tum phi mathbufta text grav beta phi mathbipes a text grav pluffa mathbibifaf hita text sesu falsine mathbefta phi text Lorentz. Thing where grav is solar gravity, is the ratio of radiation pressure to gravitational force. A Stubler's represents solar wind drag, and Lorentz captures electromagnetic effects on charged grains. For a typical carbonaceous particle of radius 10 m to zeta 0.5, meaning radiation pressure is half as strong as gravity, pushing the grain away from the sun. But for large refractory grains, 10 to 100 mm in radius, RD drops below 0.05, allowing them to remain close to the orbital plane and even project visually sunward when viewed from Earth. This explains the apparent tail, a sheet of large, slow-moving particles lying along the orbital plane, illuminated under near-zero phase angle conditions. As the viewing geometry changed, the Earth crossed the comet's orbital plane, and the tail vanished as the smaller, radiation pressure dominated grains formed a standard antisolar tail. The transformation is thus a geometric projection of physical segregation by particle size. Yet in 3IATLAS, the anti-tail's brightness was unusually strong, nearly equivalent to the main tail flux, suggesting that large particles were being ejected at substantial mass loss rates. Infrared constraints indicate hard dust M layer 200 kgs thing during peak activity. Assuming an average outflow velocity of 100 ms and bulk density of 2000 kg/m², the corresponding cross-sectional area of active emission would be about 5000 ms, or less than 1% of a 3-kilometer nucleus's surface. Such localization points to discrete vents or fractures where chyle gas escapes directly from subsurface reservoirs. Asymmetric outgassing from these vents acts as a continuous thrust source. The torque applied to the nucleus alters its rotational state. Over weeks, such torques can cause precession of the spin axis or even excitation into non-principal axis rotation, sometimes referred to as tumbling. Monitoring photometric light curves at multiple wavelengths can reveal these dynamics. In 3IATLAS, early October photometry showed a periodicity near 11.2 hours, but subsequent data hinted at phase drifts consistent with a changing spin axis, potentially induced by these CO₂-driven jets. Non-principal axis motion has strong implications for orbit modeling. Each jet's direction relative to the Sun changes as the nucleus tumbles, modulating the non-gravitational acceleration vector. The classical Marsden coefficients assume a fixed orientation, but a time-variable torque introduces quasi-periodic deviations in observed astrometry. Detecting such signatures requires dense temporal coverage, precisely the goal of the IAWN campaign, to assess whether the reported 1 million kilometer residual could plausibly arise from jet thrust. We can estimate the expected displacement from an IAWN term of 3D10 a day dollar. Over 60 days, this produces a cumulative shift of pelter to 2 at 0.5 times 3D times 1070 times a 60 rave 2 tons 0.000 force text peen, or roughly 80,000 km, an order of magnitude below the alleged offset. Thus, if the million-kilometer discrepancy is real, either the acceleration has been severely underestimated or additional forces are at work. One candidate is anisotropic mass loss during perihelion passage. If the comet underwent a transient outburst, say, the sudden venting of trapped clathrates, the instantaneous momentum impulse could generate a step-like change in orbital elements. The impulse RV required to shift position by 1500 km over a month at a heliocentric velocity of 40 km/s is about 0.3 ms/s. For a 3 km nucleus mass the 70 enough to g, this corresponds to a gas release of only 700 kg, equivalent to a few minutes of strong outgassing at the measured mass loss rate. Thus, even a brief event could, in principle, create the apparent offset. However, distinguishing between genuine momentum transfer and measurement bias is difficult. During solar conjunction, ground-based tracking suffers from elevated background noise due to coronal scattering and atmospheric refraction. Sub-arcsecond centroiding precision requires a signal-to-noise ratio above 30. Most small observatories report SPAN below 15 near the Sun, meaning systematic errors can reach tenths of an arcsecond, translating to hundreds of thousands of kilometers at interplanetary distances. The IAWN campaign's calibration with Gaia reference stars aims precisely to suppress these biases. The solar environment itself complicates modeling. During late October, a coronal mass ejection (CME) swept through heliocentric longitudes near 140 degrees, roughly coincident with 3IATLAS's position. The associated increase in solar wind proton density from 5 cm to nearly 30 cm quant amplified the Lorentz term in the dust dynamics equation. Charged submicron grains experience accelerations of the order L tum fractal m to v f times math f b if math f type n. For a grain with radius 0.5 mm, charged L10 10 g magnetic field 5nt, and velocity 400 km/s. This gives to 4 tau 10 ma 4 hour, L and 40 10 might 4 and s dog, comparable to radiation pressure. Thus, electromagnetic coupling during CME passage could significantly alter small, grain trajectories, changing the appearance of the tail without requiring large nucleus acceleration. Observations of the iron tail reinforce this view. Spectra from the Planetary Virtual Observatory (PIVO) detected enhanced CO and endo lines near 390 nm, indicating strong ionization. The iron tail's orientation deviated from the dust tail by about 8 degrees, consistent with magnetic field deflection. This divergence, while common in active comets, reached unusual magnitude in 3IATLAS, hinting that plasma effects, not purely geometric projection, contributed to the tail morphology shift. The Mars orbiter imagery, if released, may allow calibration of these interpretations. A camera in Mars orbit views the inner heliosphere from a geometry displaced by tens of millions of kilometers, providing parallax leverage. If both Earth-based and Mars-based detections of 3IATLAS are obtained at the same epoch, their positional difference directly yields the object's three-dimensional location, enabling verification of any claimed orbital offset. Moreover, the Mars geometry reduces solar elongation effects, offering cleaner background subtraction. From a compositional standpoint, CL dominance suggests that 3IATLAS retains volatile inventory from low-temperature formation regions, possibly beyond 30 AU in its parent system. Interstellar radiation over millions of years would erode superficial ices, leaving only buried pockets. Their persistence implies a protective dust mantle and low porosity. Thermal models must therefore include internal heat conduction, parameterized by the effective thermal diffusivity Li. For porous ice, dust mixtures, Lana 10 hememzines aing. The sublimation front thus migrates inward only millimeters per perihelion, meaning each outburst exposes pristine material, a key factor in the observed spectral purity of CO lines. This cryogenic resilience differentiates interstellar comets from typical Oort cloud objects, which often display HNO-dominated spectra. The volatile ratios can even inform stellar system origin. For example, the elevated CO₂-HNO ratio suggests condensation under a stellar luminosity lower than the Sun's. Perhaps an M-dwarf environment where the Keohl snowline lies closer to the star. But in 3IATLAS reappears in early November. Astronomers will test these hypotheses by measuring coma color indices and polarization. Polarimetric phase curves between 10 Briggs and 40-degree phase angles are sensitive to grain composition and size. Silicate-rich dust produces maximum polarization near 25 degrees, whereas carbonaceous aggregates peak near 15 Bri. If the returning observations show a shift toward lower polarization angles, it would confirm large, carbon-dominated grains as the source of the earlier antite tail. Dynamicists are equally focused on refining orbital elements. The trajectory remains hyperbolic with eccentricity to 1.020,000.003 E1.025 as 2003, implying an interstellar origin with excess velocity near 2 km/s. Yet small uncertainties in A today can mimic slight deviations from IAWN, so high-precision post-conjunction astrometry is vital to confirm true hyperbolicity. Should the final solution confirm real non-gravitational acceleration consistent with directed outgassing, it would place 3IATLAS closer to 2I Borisov in behavior, a typical, active comet that happens to originate beyond the solar system. If, however, the residuals remain unexplained after all physical corrections, more exotic possibilities such as high albedo anisotropy or reflective flake emission might need to be considered. For now, the scientific consensus remains conservative. The observed phenomena can be modeled within known cometary physics, albeit at extreme parameter values. Nature, not artifice, still provides the simplest fit. Yet, every reappearance phase offers a new laboratory. As 3IATLAS rounds the Sun and emerges into darker skies, its evolution will let scientists test the frontier where solid-state physics meets plasma dynamics, where micron-sized grains trace the invisible structure of interplanetary magnetic fields. In the weeks following solar conjunction, as Earth and 3IATLAS move along their respective orbits, their lines of sight gradually diverge from the Sun. The comet's apparent elongation increases from near zero to over 25 degrees by early November. This slow separation marks the beginning of the reappearance phase, a window when optical detection again becomes feasible. But the geometry this time will be challenging. The comet's elongation remains low, meaning twilight observations and stacked long exposures will be required. For most ground-based telescopes, the limiting surface brightness near dawn is around 23 magnitudes per square arcsecond. To detect 3IATLAS, observers will need exposures of several minutes under dark skies, with careful background subtraction to remove solar scattered gradients. Stacking algorithms like astrometry or PixInsight's Comet alignment mode can register frames along the predicted ephemeris, revealing the faint, diffuse coma that may otherwise vanish in noise. The expected apparent magnitude near reemergence is Fl14 to Fl15, depending on dust production. This is well within reach of mid-sized amateur telescopes, equipped with CMOS sensors, provided careful flat fielding and calibration. But the more interesting challenge is not visibility. It is precision. Astrometry from the new apparition will constrain any accumulated orbital residuals since conjunction. To first order, the positional uncertainty grows with time, as CO₂-driven, where A represents the non-gravitational acceleration amplitude. Over 60 days, even a small AL term can yield tens of arcseconds of positional drift. The IAWN global campaign is designed to minimize that uncertainty through distributed coverage, multiple observatories, diverse longitudes, but in different phase angles. Each contributes independent astrometric points tied to the Gaia DR3 catalog, allowing sub-arcsecond global fits once combined through the minor planet center. If consistent offsets appear across independent sites, they will confirm a true course deviation, the first robust non-gravitational trajectory confirmation for an interstellar comet under high solar activity. But if residuals scatter randomly with seeing conditions, the deviation claim will likely collapse into measurement noise. This is the fundamental tension at the heart of comet dynamics, the line between real thrust and apparent parallax, between physics and geometry. To interpret these outcomes, modelers rely on nucleus, shape, and torque evolution simulations. The nucleus is rarely spherical. Radar and photometric inversions show that most cometary nuclei are elongated, bilobed, or contact binaries. For 3IATLAS, brightness fluctuations before conjunction suggested a shape model roughly consistent with an axis ratio of 1.8:1, meaning the longest axis is almost twice the shortest. Such asymmetry can focus jets preferentially along specific directions, amplifying net torque. Numerical models describe this using the moment of inertia tensor and Euler's equations of rotational motion. I3 that is omega 2 omega 3 tot 1 king and its cyclic permutations. Here II are principal moments, Ni angular velocities, and Toi torques from gas emission. The resulting motion can be integrated over time using a fourth-order Runge's-Kutta scheme, tracking changes in the spin vector. Simulations indicate that a vent producing a thrust of just 20 N, offset 500 meters from the center of mass, can change the orientation of a 3 km nucleus by several degrees per week. This tumbling motion alters which regions receive sunlight, thereby modulating the activity cycle, a nonlinear feedback loop that gives comet light curves their characteristic unpredictability. As 3IATLAS reappears, one of the key observational priorities will be measuring its light curve periodicity ANU. If the 11.2-hour rotation period has shifted significantly, it will indicate sustained torque during conjunction. The combination of new light curve analysis and precise astrometry will let dynamicists reconstruct the integrated non-gravitational forces and test whether the course deviation hypothesis holds physical validity. The Mars orbiter imagery plays a central role in breaking degeneracies. From Mars' vantage point, parallax separates 3IATLAS's apparent motion by several arcminutes relative to Earth-based lines of sight. This dual observation geometry allows a triangulation of position, converting two-dimensional astrometric tracks into a true three-dimensional trajectory. If a Mars orbiter camera, such as the Mars Color Imager (MIRCY) or the Mars Reconnaissance Orbiter's CTX, captured the comet against the heliocentric background, then correlating timestamps with Earth-based measurements can directly yield the nucleus's spatial offset in kilometers, not just arcseconds. Analysts will use radiometric calibration to interpret these images. By comparing pixel brightness against reference stars and correcting for solar phase angle, one can derive the absolute magnitude of the nucleus and coma, combined with an assumed albedo, typically 0.04 for dark carbonaceous material. This gives an effective cross-section CDAL to feather 24 times 10 to 22 R2 delta 2 10 easier 0.4 midi odovi, ping where R is heliocentric distance in AU. Joda the observer distance, Mn the apparent magnitude, Mnl the sun's V band magnitude, and PV the geometric albedo. Linear numbers 14.5 my 14.5, 1.2 RP 1.2 AU to 0.8 to 0.8 AU, par 0.04 PV 0.004 yields the 15C the 15 km, corresponding to an equivalent spherical radius of about 2.2 km. This aligns with previous indirect estimates from dust production rates, suggesting the object's core is neither massive nor tiny, but typical of intermediate-sized active comets. Shape reconstruction, however, requires more than brightness. If the Mars orbiter's imaging cadence captured rotational modulation, scientists can apply the light curve inversion technique, a method pioneered in asteroid studies, to estimate the nucleus's 3D structure. By fitting observed flux as a function of viewing angle and rotation phase, the algorithm iteratively derives a convex hull that best reproduces the observed variations. The resulting shape can then be checked against thermal emission models to verify self-consistency. Thermal modeling will be crucial because 3IATLAS operates in a high-energy regime near perihelion. The energy balance equation governing the surface temperature is L1 a fracas no odit ufar 2 la to epsilon e sigma t for thalo to celododam tm, and key where a is bond albedo, and SS a solar constant, MO emissivity, ET temperature, and else a latent heat of sublimation, and mass, loss flux. For KL sublimation, velal seta 5.9700 J kz. Balancing this at 1.1 or 1.1 AU yields a surface temperature around 190 K, consistent with infrared observations. The local mass flux, hatant VAP, A features otruvai, M hem type VP N mundrus 2 av KTA, gives about 1,000 and then kimazi memodas there at that temperature, meaning an active area of ton diameter dyes can sustain a total gas loss rate of 1 ton per second. Precisely the level inferred from tail brightness. The interplay between surface temperature, gas dynamics, and nucleus shape determines jet behavior. When the nucleus rotates, sunlight sweeps across irregular topography, causing thermal lag between insolation and emission. This produces curved jets that spiral outward, tracing the rotation of the body. Capturing these spirals in long exposure images allows determination of the spin direction and pole orientation. In 3IATLAS, early images from the Subaru telescope hinted at such a spiral morphology, implying a prograde rotation relative to the orbital plane. Confirming this with post-conjunction data could solidify the rotation model. From the standpoint of population statistics, each interstellar comet offers a data point for understanding how common such objects are in the galaxy. Assuming detection efficiency of 20% for current survey capabilities and 2 confirmed interstellar objects in 5 years, the inferred local number density is about 0.1 per cubic AU. Extrapolating to the galactic scale yields roughly 10,000 such bodies orbiting between stars, a massive but diffuse population. Whether they are ejected planetesimals, debris from disrupted planetary systems, or remnants of stellar formation, each detection refines these probabilities. 3IATLAS's distinct rich composition contributes to this emerging taxonomy. 1 Oumuamua exhibited negligible gas emission and high reflectivity. 2 Borisov was highly volatile with typical cometary behavior. 3IATLAS, with its strong CO₂-HO ratio and transient anti-tail, falls between them, an intermediate evolutionary stage possibly representing an object whose surface mantling is partial, not complete. Its activity level per unit area may provide insights into thermal evolution in interstellar transit. Transit modeling suggests that interstellar exposure gradually compacts and dehydrates outer layers, forming a refractory crust several centimeters thick. Cosmic ray processing also darkens the surface through amorphization of organics. The observed activity therefore originates from deeper reservoirs exposed by impacts or stress fractures. If we quantify the surface fraction that remains active, we can estimate the degree of interstellar weathering. For 3IATLAS, the ratio of active area below 1%, A to total surface is consistent with an exposure age of tens of millions of years, long enough to cross multiple parsecs, but short enough to retain buried ices. When the comet reappears, spectroscopic measurements across the near-infrared will test this conclusion. The 4.26 mKil band and the 3.0 mHno band together constrain the volatile inventory. A shift in the CO₂-H ratio with heliocentric distance will reveal whether sublimation fronts are depleting or deepening. If the ratio remains high even as the comet recedes, it implies that the active region is CO₂-dominated and insulated from water sublimation, a hallmark of primordial layering. The polarimetric phase curve will further discriminate dust composition. By measuring the degree of linear polarization at various phase angles, one can infer the refractive index of the grains. Silicate dust yields polarization maxima near 25 Brs, carbonaceous grains near 15 Br. The earlier anti-tail favored low polarization material. Confirming this trend would reinforce the idea that large, dark grains dominated the pre-conjunction emission. As global data accumulate, analysts will feed observations into non-gravitational orbit fitting algorithms. These incorporate both solar radiation and jet thrust, parameterized by axa radial, ANS transverse, and Ali normal accelerations. The iterative fitting process adjusts these coefficients to minimize residuals between observed and predicted positions. Convergence towards stable, non-zero A values indicates real acceleration. Instability suggests data noise. By late December, preliminary fits will reveal whether 3IATLAS's trajectory genuinely diverges from Keplerian motion or not. If a true deviation emerges, its direction relative to the orbital plane will reveal the nature of the thrust. A purely radial acceleration implies symmetric sublimation facing the Sun. A transverse component implies rotational modulation. The ratio ANG can thus estimate spin orientation. For example, if ALN 0.5, but the effective jet axis is inclined about 27 degrees to the Sun-Comet line. These geometric diagnostics translate abstract numbers into physical orientation models. Ultimately, the combination of photometry, spectroscopy, astrometry, and thermal modeling will converge toward a coherent physical picture, a CO₂-driven, a rotating interstellar nucleus, active at localized vents, whose tail structure records the competition between sunlight, magnetism, and geometry. It is a small object tracing the largest gradients in the solar system, a grain of cosmic history, revealing the equations of its own decay. When the International Asteroid Warning Network's campaign formally opens in late November, observatories distributed across both hemispheres will begin submitting nightly astrometric reductions to the Minor Planet Center. Each record, time-stamped, catalog-aligned, and photometrically normalized, adds a single datum to the evolving orbit of 3IATLAS. Yet behind those faint points of light lies a cascade of physical inferences: the thrust of sublimating gases, the microphysics of dust entrainment, the shape of an object that until recently lay between the stars. Astrometric reduction begins with the raw frame, a field containing background stars, cosmic ray hits, and a moving target that may occupy only a few dozen pixels. After bias and dark subtraction, analysts apply a flat field correction and solve for the world coordinate system, using Gaia DR3 stars as references. Typical solutions achieve residuals below 0.55 arcseconds, translating to positional uncertainties under 200 kilometers at the comet's distance. These coordinates are expressed in topocentric right ascension and declination, corrected for aberration and light, time delay, and submitted in standardized MPC format. When aggregated, they define a residual vector field, each arrow marking the difference between predicted and observed position. The global fit proceeds through weighted least squares minimization of the 6 Keplerian elements, plus 3 non-gravitational coefficients CO₂-driven. The process iterates until the RMS residual drops below observational noise. If systematic drift remains, the model introduces time variable terms day dt to capture secular evolution of outgassing thrust. For 3IATLAS, early synthetic tests indicate that a constant A model cannot reproduce the expected asymmetry of pre- and post-perihelion motion. A variable AON term, modulated by heliocentric distance as ADALS XPH, provides a better physical match. These coefficients have tangible meaning. AT represents radial acceleration, directed away from the Sun, arising from isotropic sublimation. L is transverse, altering orbital angular momentum through diurnal jet modulation. AW is normal to the orbital plane, reflecting seasonal asymmetries between northern and southern hemispheres of the nucleus. In standard units of Orday-Ducko, typical values for active comets range from 10 sut to 10 Z. A confirmed A on the 3T10 Hing Orday-D for 3IATLAS would yield a cumulative displacement of roughly 80,000 km per month. Detectable, but physically reasonable given CO₂-driven jets. Photometric monitoring runs in parallel. The integrated magnitude is decomposed into nucleus plus coma components using aperture photometry with radial profile fitting. The AF parameter, defined as the product of albedos AA, filling factor F and aperture radius LU, provides a proxy for dust production independent of aperture size. For 3IATLAS, AF values near 300 cm at errata 1.2 AU place it among moderately active comets, consistent with a dust-to-gas mass ratio near 1. By tracking AFA versus heliocentric distance, observers will estimate the activity slope N in AFO-Ra. Nelly 3 would indicate strong volatile control by solar heating. Spectroscopically, narrow band filters isolate emission features of CN, CL, and CO. Comparing these fluxes yields production rates QCN, QCl, QL in molecules SE ratios QQO, QO, short 5 confirmed Kel dominant sublimation. Strengthening the inference of a low temperature formation zone. Temporal correlation between Q-Kyle and non-gravitational acceleration. A provides a direct physical calibration. Gas flow momentum balanced against the measured thrust. The campaign structure, spanning Nov 27 to Jan 27, coincides with increasing solar elongation, enabling progressively cleaner photometry. Early data near dawn will come from robotic arrays like ATLAS HKO and PAN, STAR S2. Mid-campaign observations will rely on a 1 to 2 meter-class instruments under darker skies. By late January, the comet will fade beyond magnitude CO₂-17, but by then hundreds of positional measurements will define its post-conjunction trajectory with unprecedented precision. As data accumulate, orbit solutions converge. A typical reduction pipeline, such as Find Orb or OrbFit, computes covariance matrices for all orbital parameters, outputting 1 to uncertainties. If the fit yields each or 1 by more than 3, even after applying outgassing corrections, the interstellar classification stands secure. Preliminary Monte Carlo runs suggest that unless hidden systematic biases exceed 0.5 arcseconds, 3IATLAS will remain hyperbolic with 8A1 POSO 2 to 0.1003, confirming escape velocity relative to the Sun. The derived incoming asymptotic direction, roughly R8M 8A14M, DEFN 25 Breve, points toward the galactic antique center. This contrasts with Wankengo-Muamua's Vega direction approach and Tuik-Borisov's Cassiopeia origin, suggesting random distribution consistent with isotropic stellar ejection, rather than a stream from a single star system. Dynamicists use these trajectories to estimate the local flux of interstellar objects, currently about 0.1 per cubic AU. Future surveys like the Vera C. Rubin Observatory's LSST will push detection limits 2 magnitudes deeper, potentially uncovering tens of such visitors per decade, while ground-based telescopes track visible light. Solar orbiting observatories contribute in other wavelengths. The Stiro and Saho-Lascaux coronagraphs may have recorded 3IATLAS during conjunction, though their resolution is low. Nevertheless, photometric time series from these platforms can reveal transient brightening episodes indicative of outbursts or fragmentation. Should the comet exhibit a sudden 0.5 magnitude flare, the implied mass release, on the order of 10 kilograms, would produce a measurable impulse, Stuther VD 0.3 mc. sufficient to account for large astrometric residuals. Thus, even low-resolution heliospheric imagery provides physical leverage. Understanding fragmentation risk is essential. Thermal stress modeling uses the differential equation of frac dt data 3IATLAS c.p, a nabla 2t for a frac q data tex ups ela rho c.p, quin where k is thermal conductivity, J density, c.p specific heat, and q dabs absorbed flux, large diurnal temperature gradients, often to 50 K between day and night sides, induce internal stress exceeding 100 pi. For a low cohesion body, tensile strength Thuventine path, micro fracturing can occur, exposing fresh ice and altering the torque balance. Monitoring photometric periodicity changes will reveal whether 3IATLAS underwent such events during conjunction. Meanwhile, numerical dust tail modeling provides independent diagnostics. Using the Finson-Probstein approach, each dust particle's trajectory is computed under gravity and radiation pressure, characterized by Gay. Superimposing thousands of synchrones, constant, ejection, time curves, and Sindines, constant, Bay curves reproduces observed tail morphology. Fits to early October images yielded Baymax 0.5 and ejection speeds E100 ms, consistent with micron-sized grains. Post-conjunction imaging will test whether particle sizes or velocities changed, an indicator of gas composition evolution. All these measurements flow into a single conceptual outcome: a physically consistent model linking micro-scale sublimation to macro-scale orbital change. The beauty of cometary astrophysics lies in this coupling. The way volatile molecules, liberated one by one from subsurface ices, collectively nudge kilometer-sized bodies onto new paths through the solar system. The implications extend beyond 3IATLAS itself. Each verified non-gravitational acceleration refines estimates of how frequently interstellar planetesimals pass through our neighborhood. These statistics inform models of planetary system formation and ejection efficiency. Simulations of protoplanetary disks suggest that for every Earth, massive planets retained, roughly 0.1 Earth, masses of debris are expelled into interstellar space. Most of it remains undetectable. Only when a fragment's trajectory intersects the solar system does it briefly reveal its origin through the chemistry of its coma. Looking ahead, missions are being designed specifically for such encounters. ESA's Comet Interceptor, scheduled for launch later this decade, will wait at the Sun-to-Earth L2 point, ready to redirect toward a newly discovered long-period or interstellar comet. With rapid response propulsion and modular probes, it could, in principle, intercept an object like 3IATLAS, sampling gases and dust directly. The science case for such a mission grows stronger with each interstellar detection, and 3IATLAS provides a template for target characterization, estimate activity, assess stability, and predict the encounter window. On the theoretical side, understanding dominated comets bridges cometary physics with exoplanetary science. The relative abundances of volatiles encode the chemical gradients of their natal disks. If interstellar comets display systematic differences from solar system ones, say, higher CO₂-H ratios or distinct isotopic signatures, they trace environments cooler or more carbon-rich than our own. Measuring these ratios therefore indirectly maps the diversity of planet-forming conditions across the galaxy. In the closing weeks of the campaign, as 3IATLAS recedes toward 1.6 AU, its activity will wane. The coma will shrink, the tail will thin, and the nucleus will fade back into anonymity. Yet the datasets accumulated, photometric curves, spectra, orbital fits, will persist as a numerical legacy. Each data point adds to the empirical foundation on which interstellar comet science now stands. The narrative that began with a faint streak entering solar glare will end in petabytes of calibrated data and refined equations. Whether or not the million-kilometer offset proves real, the effort to test it sharpens every tool of observational astrophysics: precision timing, multi-station parallax, plasma, dust modeling, and the physics of radiation-driven motion. This is how science progresses, through disciplined confrontation between measurement and model, between anomaly and explanation. And so, as the comet emerges once more into the cold geometry of space, its story becomes part of a larger pattern. The slow accumulation of evidence that the galaxy is filled with these wanderers, emissaries of distant suns, carrying in their vapor and dust the record of countless frozen dawns. Each time one passes near the sun, we glimpse that record illuminated for a brief season, written not in words but in spectra, accelerations, and the faint curvature of a tail that points forever away from home.